Welcome to The Explainer. Today, we are breaking down one of the most powerful concepts behind modern artificial intelligence, optimization. It's really the secret sauce that makes everything from your phone to self-driving cars actually work. Okay, so let's just dive right in with a question that gets to the absolute heart of this. In our everyday lives, we make this kind of trade-off all the time, right? But in the world of AI, where a computer could literally spend days or weeks or even years chewing on a problem to find a single perfect answer, well, this choice becomes absolutely critical. And that's exactly where this idea of an optimal solution comes from. Look, it's not about being wrong, it's about being smart and efficient. For really complex problems, trying to get the exact 4.000 answer can take way too long and burn up way too many resources. So instead, we aim for something that's incredibly close, like 3.98, but we find it in a tiny fraction of the time. This is the practical choice that really makes AI possible. So here's our game plan for this explainer. We're going to build this idea from the ground up, starting with that core concept of optimal versus exact. Then we'll see where it came from, how machine learning uses it, and wrap up with how it's powering the world all around you. All right, first up, let's really get into this fundamental choice. It's this constant tug of war between getting something absolutely perfect and just, getting it done. What's so important here is it really lays out the why. For a simple problem, sure, we want the exact answer. But for the massive, messy, super complex problems that AI has to tackle, like understanding human language or identifying a dog in a blurry video, chasing that perfect answer isn't just slow. A lot of the time, it's functionally impossible. The optimal solution is what actually gets the job done. You might think this is purely a computer science thing, right? But here's a pretty cool piece of history for you. This idea wasn't born in a server room or a tech lab. Its roots are in a much more physical, industrial world. And this is the origin story. Just picture a factory floor. The managers were obsessed with one single question. How do we get the absolute most product out of our assembly line for the least amount of money, using the fewest resources and the least amount of time? They were trying to optimize their whole process. And here it is, the aha moment. The logic is exactly the same. We just swap the words. In a factory, you want to minimize cost and maximize profit. In machine learning, we want to minimize the model's error and maximize its accuracy. See? It's the same core idea, just applied to data instead of, say, cars or widgets. So, how does a machine actually do this? How does it apply that principle of minimizing error and maximizing accuracy? This is where the magic really starts to kick in. The key thing to get is that we don't rewrite the whole program every time it makes a mistake. Instead, every machine learning model has these things called model parameters. Seriously, just think of them as a bunch of adjustable dials or levers. For a simple line on a graph, those parameters are its slope and where it crosses the axis. Just by tweaking those dials, we can totally change how the model behaves. And this is that optimization loop in action. Step 1, the model makes a guess. Step 2, it measures how wrong it was, we call that the error, and it uses that to make a tiny adjustment to its internal dials. And then, step 3, it makes a new, slightly better prediction. It just does this over and over and over again, thousands or even millions of times, getting a little bit smarter with every single cycle until that error is as low as it can possibly get. But of course, there's a twist. It turns out that just hammering that error down to 0 on your training data isn't actually the goal. There's this really delicate balancing act you have to pull off to create a model that's genuinely smart. So on one hand, if your model's too simple, it underfits. It's kind of like trying to draw a really complex, curvy shape using nothing but a straight ruler. It just completely misses the real trend in the data because it's not flexible enough to learn the actual pattern. But then you've got the other extreme. If your model gets too complex, it overfits. And this is such a classic trap. Think of it like a student who just memorizes all the answers for the homework, including the teacher's typos, but hasn't actually learned anything. They get a perfect score on the homework, right? But then they totally bomb the final exam when they see new questions. So the sweet spot, the real goal, is what we call a good fit. This is a model that's complex enough to learn the important patterns, but not so complex that it just memorizes everything. It can generalize what it's learned to new situations it's never seen before. And that's the mark of real intelligence. And there's actually a pretty solid rule of thumb for this.
A good fit model is generally considered to be one where the performance gap between the data it trained on and new data it's never seen before is no more than 5%. If that gap gets much wider, you're probably dealing with an overfitting problem.
Okay, so with all that in mind, let's see how this whole concept scales up into the technology that really dominates AI today, deep learning.
Deep learning is basically a supercharged version of everything we've been talking about. It uses a structure called a neural network, and really, deep just means it has lots and lots of layers. Remember those two little dials on our simple line model? Well, a deep learning model can have millions, sometimes even billions of these dials, all getting tuned at the same time. And it's that incredible scale that lets it take on these insanely complex problems.
Think of it kind of like a specialized assembly line. The raw data, like all the pixels in a cat photo, goes in one end. The first layer might just look for simple things, like basic edges. The next layer takes that info and looks for combinations, maybe corners and curves. The layer after that might recognize things like paws and whiskers, until finally, the output layer puts it all together and makes a prediction. Cat. Each layer is optimizing to find a more abstract feature, building on the work of the layer before it. And this is exactly why deep learning has become so dominant. It just thrives on a scale that would completely crush older methods. It can learn from millions of examples, handle all sorts of messy data, and this is a huge one. It can figure out the important features all by itself, which is a task that used to take data scientists weeks or even months of manual work. So let's bring this all back home, because this isn't just theory locked away in a lab somewhere. This whole process of optimization is the engine running silently behind countless technologies you use every single day. That speech to text on your phone? Yep, that's optimization. AI helping doctors spot tumors in scans? Optimization. Self-driving cars, chatbots, your Netflix recommendations, facial recognition, even the characters in the video games you play. They are all powered by this exact same process of constantly tweaking those dials to minimize error and get as close as possible to the best answer. And this all leaves us with one final massive thought. We've built this incredibly powerful tool that can learn and improve at pretty much any task we give it. So the biggest question is no longer how we solve problems, but deciding which problems are the most important for us to solve next. What do you think we should point this engine at?